The next keynote is by none other than Dr. Ben Goertzel. It could be called the father of AGI. Definitely coined the term.
Since I jumped into the AI field seriously in the late 80s, I got my PhD in 89, my reaction to the disparate collection of methods in the AI field, I mean, you had already back then, you had deep neural nets, although they weren't labeled with that. They were multi-layer perceptrons and whatnot. You had deep neural nets, you had symbolic AI systems, you had evolutionary learning since the 1970s, right? And you had a disparate collection of AI methods, each of which seemed to capture something about how intelligence worked, and each of which seemed better at doing certain sorts of things than others. And making that observation, there were a couple directions you could go. One is you can say, well, can I come up with some cosmic theory or mechanism from which all these different symbolic neural evolutionary things are like a specialization? The other thing you can think is, well, let's just wire them all together, right? Like take one system that uses evolution when it needs to, logic when it needs to, deep neural net when it needs to, and connect them all together. And you know that the mathematical part of my brain wanted to unify them all into one thing. The practical engineering part of my brain is just like, okay, these each do something useful. Let's just wire them together, like you wire together, you know, an engine, a carburetor, a drivetrain, right? And then you get a machine that will do all the kinds of things that it needs to do. And I would say since that time, I've been pursuing a sort of combination of those approaches, right? The WebMind AI system in the late 90s that Charlie, Matt, and I, and Mike a little bit, and a whole bunch of others worked on, and Pei Wang was part of that. Also, we had NARS in there at the time, and that work is what spawned PLN as an alternative to NARS as a logic system. I mean, there, it was really more of a multi-agent system where neural and logic stuff were separate and communicating with each other. And as we create a series of hybrid systems, we've tried to move more toward unification of different AI methods. So in the Hyperon system that I'll talk more about in my contributed talks after the break, in the Hyperon system, we have this one meta-representational fabric, the atom space, which is a metagraph. Then you can put logic in there, you can put neural nets in there, you can put evolving programs in there. And you could view it as a multi-agent system, but we're more trying to get a common representation for different methods. But that, even if you have a bunch of methods implemented in a common metagraph, though, you still have the question, how can we unify the kinds of learning and reasoning that they're doing, right? And it's not a given that you need to unify them completely. I mean, like the brain has a common infrastructure of neurons, synapses, glia, astrocytes, blah, blah, blah. But I mean, there's different brain cells in different parts of the brain doing different sorts of things. So, I mean, everything doesn't have to be one grand unified thing. You can have a heterogeneity of things interacting with each other. But it's still interesting to see how much unity you can get, right? And that's really what inspired the work I'm about to present here. I mean, I've been drawn for a long time to Occam's razor type heuristics and minimum description length and other ways of thinking about simplicity of modeling, and that has seemed like a concept that spans many different kinds of AI, like logic, neural nets, program learning, blah, blah, blah. And I'd written a few papers over the years trying to find the right way to sort of summarize, like, what is a simplicity, what is an Occam-like prior or bias that you could formulate in a really general way and apply across the scope of learning algorithms, because that would go some way toward giving like a grand unified understanding of all these different AI paradigms and methods, each of which serves to serve seems to serve its own role in achieving human-like cognition. So, when I saw Michael Bennett's talks on weakness at the previous AGI conference, it seemed like it had some promise. It was more elegant than minimum description length formulations, although I like Kolmogorov complexity and algorithmic information quite a lot also. And I started to think about how you could apply Bennett's weakness method to the different AI methods that we're actually using in the Hyperon architecture. And then I realized that would be much less messy and more elegant if we generalize Bennett's notion of weakness a bit, and then I introduced some category theory there. And if you have sort of quantales and enriched categories, you can come up with a notion of weakness that applies in a more abstract setting, which then makes it much more immediate to apply it to logic neural nets, support vector machines, and a bunch of other concrete AI methods. So anyway, that's what I'm going to talk about for the next half hour or so. It's a pleasure to be giving a talk about something other than like the Hyperon or OpenCog architecture. However, after the break, I will give a new version of that as well. But then integrating some of this weakness material into the story, right? So this is inspired by the general concept of Occam's razor, and Michael Bennett and I have been going back and forth a bit over the last few days about how weakness relates to Occam's razor and sort of the right terminology to use here. I tend to be more math-oriented and not that concerned with the sort of English or Latin word sense disambiguation, but just to avoid confusion with Michael's talk, I will try to clarify how we're kind of using the same math, but using some words a little bit differently. But what William Occam said originally was this, which my Latin isn't very good, but basically plurality should not be posited without necessity. So that's pleasantly vague, right? And it's not exactly MDL, but I mean, you can interpret it in a lot of ways. And of course, he wasn't the first one to say something like that, right? I mean, you go back further, this was like core in Chinese philosophy. My Putonghua is bad. It's like Da Dao Zhi Jian or something. But what that means, the big Dao is simple, right? And that third Chinese character there means either the ultimate or it means approaching. So we've got even added level of ambiguity of Chinese language in there. But the concept was there. Like, you want to be simple and you don't want to introduce extra nonsense any more than is merited, right? Like that's the Wu way, like the effortless path. Don't introduce too much extra. It feels weird to call it Lao Tzu's razor because of his hairstyle. He obviously did not use a razor, right? But the point is these general concepts have been around for a while, and if we go back to Michael's excellent talk a few minutes ago, he introduced the notion of weakness, which is basically, to gloss it a bit, if you have some data, you have a bunch of explanations of that data, then the explanation that would be true in the most possible worlds is the better one, because it's making less commitment. You don't want to make any unnecessary commitment. You don't want to accept any unnecessary constraint beyond what is really needed for the data. And minimum description length is a different incarnation of this vague Occam's razor notion. Like, if you have fewer bits in your description, there's fewer distinctions encoded, right? And what I wanted to do in the math I'm going to present in this talk is find an algebra that captures these and other sort of intuitive concepts of simple or minimal explanation, but in a way that's so elegant and compositional, right? And Michael and I and then others have different interpretations of what is an Occam bias or what is simplicity, because these words are fuzzy, but hopefully the math at least is clear, right? So to roll to roll into it then, so we're starting with a commutative quantale, which is basically a complete lattice with a monodal product and a join. So I mean, pretty much you just have a plus and a times with and then a partial order, a less than, right? And then the fun is you can define these plus and times differently depending on what AI algorithm you're trying to model simplicity. So if you're dealing with an SVM, you want to define plus and times and less than one way. If you're dealing with a logic system, you want to define plus and times and less than another way. The abstract algebra is the same, and then the abstract definition of weakness is the same. So the first version of weakness I'll present is here. So you have this commutative quantale, and then you have a evaluation. So you make an enriched category with a sort of measure on top of it. And then we define the quantale weakness this way. So it's basically a sum of products, which is a very nice thing to have from a practical AI context. Like you can do a lot of nice things with sums of products that actually can tie in with Bayes-Net style message passing and so forth. So roughly speaking, it measures how many pairwise distinctions among elements the relation fails to make, right? Now, you're weighting the pairwise distinctions with this measure, so it's like, how important are the pairwise distinctions it fails to make? Because distinctions are binary. You want to distinguish as few things as possible. You don't want to make any more distinctions than you have to. Now, if folks are familiar with Spencer Brown's laws of form, which was influential on me decades ago, there's a philosophical connection there that I won't go into here. But I mean, the basic notion is the weakness is high. The weakness of some set of relations is high. When the set of relations lumps together many high-value pairs, it's weak because it commits to fewer distinctions between high-value pairs, right? And it starts to look very natural after you look at it for a while. It may not be immediately evident why it captures Occam's razor, but when we go over a few examples, it will become clear. So just to connect with Michael's stuff, hopefully a little more clearly before going into the details and applications. So what Michael called W max is basically like how many possibilities remain, how little constraint is there. MDL is syntactic, how many bits or parameters to describe an explanation. And that is how Occam's razor has most commonly been interpreted in technical fields. That's what Michael called SIMP-max. And you then have some mathematical relations that show that these are proportional. Like if you have a language which has, it's a prefix-free code, there's no dead code. And if you have a finite vocabulary language without dead code, right, then you can show a proportionality between W-max and SIMP-max. And Michael mentioned this also. So you can show some nice theorems that in an appropriate language, the explanation with the shortest expression is the explanation that's true in the most possible world. And I mean, that's nice math. Michael did that in a certain way in his thesis. You can run through the math in different ways. I'm not going to give the proof here, but it's not super complicated, right? It's pretty, and that's why MDL works to capture the semantics of weakness, I think. Then Michael talked a bunch about the stack, these hierarchical layers of sort of granularity. There's some fundamental meaning to this hierarchy. From this quantale perspective, you can just represent each level of granularity as a different quantale if you want to. So I mean, a hierarchy of algebras is one way you can relate different algebras, and in each algebra you have a sort of weakness. And so his SIMP-max, weakness max, and scale max, I mean, these are just, they come from different quantales and different measures within this more general formalism. And the scale max is a perfectly reasonable quantale to form. It's not equivalent to constant max or W max, and whether you want to call it Occam's razor or not, I don't know. We can make a time machine, go back and ask Occam, right? It kind of has the same format, but it is saying something different, right? So yeah, Zara posited some years ago Zarathustra's razor, which is when in doubt, assume the most entertaining hypothesis, right? So if as Goertzel's razor, all right, Goertzel's razor. Yeah, we have Bennett's razor. We need Goertzel's razor. Goertzel's razor, when in doubt, assume the most entertaining hypothesis. So what was interesting is when I was asking GPT-5 Pro to help make this presentation, it replaced the Goertzel's razor with resource scaling automatically. It was just like, this is too silly. We're not going to have entertainment. We're going to put resource in here, right? And I probably was right. I mean, my own entertainment or Zara's entertainment is one among many resources you might consider, right? But the thing is that the scale max does fit within the overall framework of Quantale weakness. I mean, you're just you're defining your measure to be my entertainment or whatever resource you care about. That's just different than your measure being description length or the number of worlds that satisfy some hypothesis. The resource scale has not been a Quantale of so much interest to me. There are other ways to take into account resources, but one amusing thing here is, while Bennett's definition of weakness over a Quantale of finite sets basically corresponds with MDL, if you have a different Quantale, you can sort of say how weakness in any commutative Quantale corresponds to minimum description length in some language, but the language isn't a one-dimensional series of terms, right? I mean, the language is the language is just a bunch of expressions in the free commutative Quantale, right? So you're just like glomming together plus and times, and then you can define how big is the conglomeration of plus and times that you've formed. So if you define description length in this very general way, as like basically the size of this glomming together of pluses and times, I mean, then you can prove similar results to the correspondence between set theoretic weakness and description length. It's just, you don't have a one-dimensional language. And of course, for an AGI, that's okay. An AGI can communicate in data structures with each other, right? So pretty much with any Quantale weakness over any Quantale, it does correspond with MDL over some language. It's just the language doesn't have to be a conventional language. It's an expression in a free Quantale, right? And you can connect this closely with what Ellerman called logical entropy. So this is not Shannon entropy, though it's related. The logical entropy of a partition measures the percentage of pairs of elements that lie in different partition blocks, right? So if you measure entropy that way, that's basically 1 minus the Bennett weakness, right? It's kind of a different way of looking at the same thing. The logical entropy counts the percentage of distinctions made. The weakness measures the percentage of distinctions not made, right? But Ellerman didn't posit this as a sort of universal learning heuristic. I don't think he saw the full importance of the formula, but it is a similar formula. And I mean, if you go through Mike Stay and John Baez's paper on algorithmic thermodynamics, and we have Mike Stay at this conference as well, and it's been a lot of fun and a privilege to work with him on some of these things recently. But I mean, this ties in here also. I mean, you can define an information theoretic weakness as 2 to the minus the mutual information between the hypothesis and the observed data, and I mean, then you can basically run through Baez and Stay's connection between algorithmic information and and entropy, and that just becomes a different way of looking at the weakness MDL connection, right? Because what Baez and Stay showed there is that algorithmic information is Shannon information if you have an information source that's encoding things in the right way. And I mean that same thing holds here, right? A strong hypothesis has a high mutual information to the data, a low informational weakness bakes in the data. It makes many distinctions and fits few cases. So I want to slow down just a little bit and go over some of the applications of this to AI algorithms of interest to me in a Hyperon context. And then I will jump back to the general weakness theory at the end after sort of showing why this is interesting from an AI perspective. So to apply this to formalize the kinds of logic that we're dealing with in Hyperon, one way to do it is to look at a product quantale. And you can set this up in a lot of different ways. This is just one simple way. I mean, so you can set up a quantale for logic expressions. And you can do it very simply like this. You could do it with a Heiting algebra, which is a slightly different lattice. And then you set up a quantale for truth values. And PLN simple truth values, there's a certain arithmetic you can use for adding and multiplying simple truth values, which are strength, confidence pairs. You can add and multiply them in a certain way. If you have probability distribution truth values, you can represent those as matrices. You can add and multiply them in a certain way. But you have a product quantale of logic expressions and truth values, and then you're basically doing an abstract form of plus and times in there, right? Like for the logic expression, the plus and times or an and. In the truth value expression, then the plus and times are truth value combinations. And there's some mess here because there's some independence assumption underlying the uncertain truth value combinations. And I mean, I worked this out for PLN, which is a probabilistic logic we use in Hyperon, which basically has a specific algebra for truth values. And if you were doing NARS has a different specific algebra for truth values, right? And you can look at, say, a pair-consistent logic, like constructible duality logic, and which tries to model things that can be true, false, true and false, or neither true nor false, right? And in this case, you get a different algebra for truth values. And I mean, that's all fine. The nice thing about working at this level of abstraction is a lot of the math is the same because they're all commutative algebras with some measure, right? And if you define the weakness across a product quantale, it just decomposes. So I mean you have a sum of products of logic expressions, sum of products of truth values. So in the simplest case, the logic component of the weakness is the union of overlaps in the world sets you fail to distinguish. The truth value component kind of tells you how strongly you fail to distinguish those worlds, right? And one thing that we seem to get out of this is some fun and general ways to do inference control. So if you work ever with Bayes nets, the way that you update Bayes nets in practice is manipulating all these sums of products, right? And you're just munching around these parentheses among these sums of products. And you can do that where your sum and product are in a commutative quantale. It doesn't matter. It's still a sum of products with the same rules. So the result is that you can do Bayes net style factor graph manipulation in PLN or NARS or constructible duality logic or whatever you want, as long as you have that commutative quantale over an enriched category there, right? And you can also integrate. So all the factor graph diagrams in the messaging you do in Bayes nets, they all work in this much more general setting, and you can then use weakness to do pruning, right? So you don't have to pass every message. You can not bothering to pass a message that seems not to encode a weak hypothesis according to your underlying logic, right? And Adam van der Vorst and I have been working on, mostly him, but a little bit me, and been working on an efficient implementation of this sort of abstract message processing within MORC, which is a very efficient metagraph data structure that we're using underlying the Hyperon atom space. So this is a case where having a nice abstract formulation that covers many different logics, it lets you actually put a concrete AI reasoning algorithm in place in a way that's both very fast and scalable and intrinsically covers many different logics, right? Like you can use our MORC atom space factor graph software, and if you want to swap out one logic for another, it's just some function calls for like what's the end, what's the or here, replace that, and then let the thing go, right? And you can do something similar with chaining-based inference, which sometimes is more useful than factor graph-based inference. I mean, if you're doing conventional backward chaining-based inference, I mean, you can use weakness to prune the inference tree, obviously. Like if a hypothesis seems to have poor weakness according to the quantale associated with your logic, then you just don't expand the tree in that way, right? So here we see a concrete use. Now, something we're not using in Hyperon, but I thought was interesting is if you set up the measure in the right way, I mean, then you can get the weakness to come out to the SVM margin, right? So if you've ever worked with support vector machines, I don't want to go into the math of it, so I mean, support vector machines, you're trying to distinguish pairs of points by projecting them into an infinite dimensional space using some kernel function, find a separator between them in the infinite dimensional space, then project back down. The margin is like between your points on one side of the separator and the points on the other side of the separator, like how far away are they from the separator, right? So it's some nice function analysis in reproducing kernel function Hilbert spaces. What's cool is if you set up the measure right, I mean, then the max margin in SVM, the margin is just the weakness according to that measure. So I don't know what this gives you for SVMs, except just a different way of saying things. I haven't really dug into it a lot, but I think if you're using like deep kernel learning with SVMs, where you're training a deep neural net to be your kernel function, if you used weakness instead of MDL as a regularizer for using the deep neural net inside the deep kernel function, then you can sort of you can do something compositional, right? Because you have the weakness regularizer in using your deep kernel function, and then you have weakness, which is the SVM margin. It seems nice to have one simplicity criterion to pass between the SVM and the kernel, but we're not really using that now in anything I'm doing. No. You can do the same thing in a quantum context, which is also interesting, right? So here you have actually this is not the most recent version of my slides, but it's all right. I think all I changed was the ordering. So let me see. Oh yeah. So this should be before that. So you can do weakness in a slightly more general way if you want to. I mean, the sum of products is nice, right? But in some cases, instead of a product, you want a joint measure in there, and it turns out most of the interesting things you want to do are the same whether you have a product or a joint measure in there, and that one example of something you can do with a joint measure rather than a product is you can put various biases in there. So like the philosopher Charles Peirce had the concept he called the tendency to take habits, which he called the one law of mind, right? Which was, I mean, he was writing in the late 1800s. That was a cooler thing to say then. The idea was when a pattern has been observed many times, you assume it will occur again, but even with a higher probability than Bayesian inference would tell you. Now, interestingly, in physics, Lee Smolin posited the same idea. He called it the precedence principle, and he used it as one among many axiomatic foundations for deriving Schrödinger equation, right? So without going too deeply into the philosophy or physics there, like if you want to, you could add a sort of tendency to take habits term, right? You could say your measure of the combination of U and V, you get the product, plus you add something else, which is some regularizer term times the amount of co-occurrences you've seen of those. I mean, it all still works. The reason I introduced that now is if you want to do weakness on quantum systems, and we had a bunch of nice talks yesterday on quantum AGI and so forth, right? If you want to do weakness on quantum systems, then basically the exponential of this cost function is your joint measure, and you can't factorize. So to do this in the quantum sense, use what's called the Schrödinger bridge as your monoidal product, and it doesn't necessarily decompose nicely into a product, because you have the logarithm of the sum, and I'm running out of time, so it's too much to go into. But the thing is, you can get a nice definition of a quantum weakness here, and then you can take this further. You can say, okay, take the Schrödinger equation as a boundary value problem with the past and the future, so like a history and destiny. You can then say, try to find a geodesic in the weakness geometry. Try to find the locally shortest path in the weakness geometry from history to destiny, right? And this just becomes an alternate way of looking at stationary action principles in physics. So the minimization of weakness, if you generalize it into a Schrödinger bridge quantale, it basically just gives you the minimization principles guiding physics, which is also very pleasant. And then you can set up a quantum quantale differently using positive operator value measures, and then there's a morphism from a quantum quantale using the POVMs to the one using the Schrödinger bridge, and depending on what you want to do, either one could be more interesting, right? Now, there's other specific examples you could go through. You can do weakness in hypervector space. You can do a bunch of things. But let me come back for a moment to the general theory now, having gone through some particular examples, right? And the notion of Occam's razor, broadly speaking, is that the hypotheses that commit to less, that are simpler, smaller, however you want to weigh it, will generalize better, right? And Michael Bennett showed that of his definition of weakness in some ways in his thesis. Now, there are many ways to formalize this. One way to look at it is in terms of link prediction, right? So you have a bunch of nodes. You have binary relations between them. You define weakness, and you can use the joint measure. You don't need the sum of products to get this result. So you can say, let's take this collection of nodes and links. Let's remove some of the links, and let's see, can our hypothesis regenerate those removed links correctly? So you're doing link prediction, and the result you can prove is that if you sample the withheld test links uniformly from the collection of withheld ones, then you try to predict using the joint measure which links are really there or not. I mean, the weakness basically gives you the expected accuracy, right? So this is not remotely surprising, but it holds in a general quantale context, and it then gives you the sense in which weakness does imply generalization, right? And I mean, you can go. I think I'll skip some of this due to lack of time. So what I just skipped, I will post later. But basically, you can come up with a version of universal AI similar to AXE or Gödel machine or something, which is just based on this, right? I mean, basically, you have an organism that's perceiving a stream of perceptions, actions, and rewards, and it looks for the weakest hypothesis that would have explained the rewards it got in the past. It assumes that weakest hypothesis, and it chooses the hypothesis that uses to choose its next action is drawn from the weakest hypothesis. It draws the next action and keeps going. So you can basically do an AXE type thing where instead of using algorithmic information to find the shortest program, you're using quantile weakness to find the weakest program, and you can do an AXE type thing using any quantile weakness instead of minimum description length, and it all works just as well and just as badly, right? Like it totally solves AGI for you. You can write a solution to superintelligence in like 6 lines of code, which, however, will use insanely much computational resources, so it's totally useless. But you can regenerate that in an arbitrary quantale, right? But let me wrap up though by going back to more practical AI systems that we can actually build with a tractable amount of resources, right? So what I've tried to do is embody the abstract structure of Occam's razor in a broad-ranging way. So like you can pick your substrate, pick your community of algebra and measure, and get an associated notion of weakness, and then that gives you an Occam's razor heuristic for your specific domain, and you do that differently for logic inference, you do that differently for SVM, you can do that differently for hypervectors and so forth. And the composability is neat because it means if you have 2 different AI algorithms that are working together, and maybe you need a different quantale to elegantly measure weakness for this logic engine or for this neural net or this SVM, if these different AI systems are all interacting together, you still get a composed notion of weakness among the interacting systems, right? So that's a rough recipe to use weakness in practice. I mean, you find the quantale that matches your domain, and then somewhere or other in your AI algorithm, you're inserting like, let's minimize weakness while fitting the data, right? So, I mean, in proof search, you want to prefer proof with lower weakness. For program synthesis, weaker programs should be more general, reusable code, right? I mean, if you're measuring attention, then you can use weakness to measure basically Hebbian strength of interaction. And I'll go into this a little more in my next talk, but it should be fairly clear for those who know the Hyperon or OpenCog framework how you would use that here. I mean, in inference control, you can rank different derivations by weakness. I mean, in evolutionary learning, you have an Occam bias already standardly. So this is a different way of doing the Occam bias, right? And for motivation, if you're doing goal decomposition, you want high weakness subgoals, which sort of, in a way, is the same kind of thing Richard Sutton was looking at actually in his talk yesterday in terms of goal decomposition. He was just in a much more particular numerical framework. And I'd say in terms of the notion of cognitive synergy, of getting various different AI algorithms to work together well and share their intermediate state as they cooperate to solve problems, having a common weakness heuristic with a composable algebra across the different cognitive processes, it makes it more semantically straightforward to understand how these algorithms are interoperating with each other. And I think I'm out of time, so I will skip the stuff at the end, but I'll tell you what it is, and I'll distribute these slides later. So you can use this to create a nice algebra of patterns. So if you define h of yz to be that product, you can define what it means to have a pattern in a substrate. You can define what an emergent pattern is. You can look at the algebraic rules of patterns. You can then take derivatives of patterns, and you can set up differential equations of patterns on a space where weakness is defined. So if you can then do gradient descent on patterns in systems. So it's like a pattern in a bunch of data is basically a weaker explanation for that data. And you can then do something like, you can do gradient descent to find the weakest explanation of that data, where the gradient descent is the McBride derivative on the quantale. So it's a different sort of category theoretic derivative. But using this level of abstraction, just like you can do gradient descent in numerical variables, you can do gradient descent in the quantale to find constructs that are patterns according to weakness in whatever your data is. And that lets you lift gradient descent out of the numerical realm into the symbolic realm in a quite general sense, which probably deserves a whole other talk, but it does illustrate the value of abstracting things in this way. And then in my next talk after the break, which is based on a couple of my contributed papers in the proceedings, I'll explain a little about how some of these things can be worked into the Hyperon design in particular. Thank you.